In this video, we will talk about the cylindrical transformation in multiple integration for three variables. So the first example is asking us to find the volume of the solid inside both the sphere x squared plus y squared plus z squared equal to 36 and x minus 3 whole square plus y squared equal to 9. So let's first try to understand that with the diagram. So you have this sphere which is x squared plus y squared plus z squared equal to 36. So the sphere of radius 36 units. Radius of the sphere will be 6 units. That's the outside boundary. And the inside boundary for the volume that we wanted to find out is the circle on the plane, on the xy plane, at the center at the point 3, 0. So I'm looking at a circle which is of some sort of shape like this one with the center here. So what we have understood so far, that in order to understand the limit of the integration, it is going to be easier for us if we go and take the projection of this figure on the xy plane. So let's think about the xy plane, your y-axis and your x-axis. First and foremost, you have this bigger circular projection of the sphere, which is x squared plus y squared equal to 36 when z is equal to 0. And then you have the circle x minus 3 whole square plus y squared equal to 9, which is centered at 3, 0. And this is going to help us understand the limits for x and y and z, or in terms of the cylindrical coordinate. Remember, the cylindrical transformation are x equal to r cosine theta, y equal to r sine theta, and for z, we said z equal to z. So what is happening with z? If I look at my three-dimensional figure, z starts at the z height 0 because it is bounded by the xy plane. It cannot go under the xy plane, so z is equal to 0, the lower limit. Upper limit is going to be on the sphere. How much is z on the sphere? Well, how do I know that? I'm going to set x squared plus y squared plus z squared equal to 36 and solve for z. So I get z squared equal to 36 minus x squared plus y squared. Now look at your cylindrical coordinate system. X squared plus y squared is equal to r squared. So z squared is equal to 36 minus r squared. So absolute value of z when you take the square root is square root of 36 minus r squared. Since z is greater or equal to 0, it's bounded by the xy plane. So z is greater or equal to 0. So I will take the positive value of z. So z is going to be square root of 36 minus r squared. In turn, now I know the limits for z. Z is going to be between 0 and square root of 36 minus r squared. So now we are going to find out the limits for r. So remember, r is going to be the radius of this smaller circle. So the values of r will be bounded between the circle, the smaller circle, and the center of the smaller circle. So r is going to be between 0 and whatever is the value on the boundary of the smaller circle. So how much is the value of the r on the boundary of the smaller circle? How do I find it? Well, this is x minus 3 squared plus y squared equal to 9 as the smaller circle. X is equal to r cosine theta, so I get r cosine theta minus 3 whole to the power 2 plus r sine theta whole to the power 2 equal to 9. So what I get? I get r squared cosine square theta minus 6r cosine theta plus 9 plus r squared sine square theta equal to 9. So you can subtract 9 from both sides, and this r squared cosine square theta, r squared sine square theta together will give you r squared. So r squared minus 6r cosine of theta is equal to 0. So I get r squared equal to 6r cosine theta. Since I'm on the boundary of the circle, r is not 0, so I can divide both sides by r and get r equal to 6 cosine theta. So that gives you the limit of r. It's between 0 and 6 cosine theta. Finally, for the limits of theta. Now remember, theta is going to be the circular portion So you need to understand one thing. You start at theta equal to 0. You go all the way to pi. This is the positive area. But when you go under the x-axis, you get the same area, but it is becoming negative. So in order to find the area of something which is symmetric about the x-axis, I cannot ever do the integration over the entire domain of the integration. Remember that thing? So what I do, I say that the integration for the circular portion, the theta measure, the limits are between 0 and 2 pi. But when I actually do the integration, I do the integration. So I'm going to remind you, do the integration between 0 and pi and multiply by 2. This is very much important that we remember and understand. Otherwise, the symmetry about the x-axis is going to cancel the area on the top and area on the bottom, and you will get 0. So that's not what you want. So we're going to start working on this problem now. So I have all the limits. Let's rewrite the volume function. So the volume is integration 0 to pi, as we said, 2 times 0 to 6 cosine theta for r, 0 to square root of 36 minus r squared, and then dz, dr, d theta. One other thing, don't forget, you need this r that comes from the Jacobian. Remember, from the transformation, the Jacobian is the determinant delta x, delta r, delta x, delta theta, delta y, delta r, delta y, delta theta. And what you get out of this thing, you get, when you derive r cosine theta with respect to r, you get cosine theta. R cosine theta with respect to theta, you get minus r sine theta. R sine theta with respect to r, you get sine theta. And r sine theta with respect to theta, you get r cosine theta. And that's the determinant. So I multiply diagonal wise, get r cosine square theta minus r sine square theta, which is r, if you factor out, cosine square theta plus sine square theta, and I'm pretty sure you have seen this in 14.3 and just wanted to remind you that thing. And this is that r that I need for the cylindrical transformation. Now I start working on the integration. So I get 2 times integration 0 to pi, integration 0 to 6 cosine of theta, and then I do r times z, 0 to square root of 36 minus r squared dr d theta. And the next step I will put in the limits for r, so we'll get 2 times integration 0 to pi, integration 0 to 6 cosine of theta, r times square root of 36 minus r squared dr d theta. So this is our first substitution situation. Now we are going to substitute 36 minus r squared equal to a new variable. And let's go ahead and say that this is t. So minus 2r dr is dt, but my antiderivative has r dr only. So I divide both sides by negative 2. And the other thing is taking care of the limits from r to t. R can be 0 or it can be 6 cosine theta. If you put r equal to 0, you get 36 minus 0 squared, which is 36. If you put r equal to 6 cosine theta, you get 36 cosine square theta, and you factor out 36, you get 36 sine square theta. So these are the new limits for your variable t, and you will rewrite this integration one more time. So I'm going to go ahead and say that this is 2 times integration 0 to pi. That portion doesn't change. The portion for r changes, becomes 36 to 36 sine square theta. You have r dr and square root of 36 minus r squared, which is square root of t, and r dr is minus dt over 2, and finally we have d theta. So at this point we're going to take this minus 1/2 out, and I'm going to get minus integration 0 to pi integration square root of t, so square root of 36 sine square theta, which is 6 sine theta. And I'm so sorry. So square root of t, you can think of that as t to the power 1/2 first, and then we will talk about what I started talking about. And your limits are 36 to 36 sine square theta dt d theta. So let's do the antiderivative now. So you get minus 0 to pi. t to the power 1 half will become t to the power 3 halves over 3 halves, and limits are 36 to 36 sine square theta and d theta. So what I will do, I will bring this 3 halves outside and it will become minus 2/3 antiderivative 0 to pi. 36 sine square theta, when you take the square root, it becomes 6 sine theta, and then you take the third power of that and it becomes 216 sine to the power 3 theta. Similarly, minus 216 as well. And I'm going to write it as two separate integration. So I will get minus 2/3. The first one is 0 to pi. 216, the sine square theta, I'm going to write it as minus 1 minus cosine square theta. And then sine theta. So you have sine square theta times sine theta. I wrote it as 1 minus cosine square theta times sine theta. And then I have the second integration, which eventually will become plus 2/3 integration 0 to pi 216 d theta. All right. So we're going to simplify. Take this 216 out. 2 times 216 is 432 over 3. So negative 0 to pi, and I get sine theta d theta, and negative is positive, 432 over 3, antiderivative of cosine square theta sine theta d theta, and finally plus 2/3 times 216 times theta between 0 and pi. So 432 over 3, if you divide it by 3, you get negative 144. Antiderivative of sine theta is minus cosine theta between 0 and pi. For the second one, I actually need a little bit of substitution back again. And this time I will substitute cosine of theta is equal to, say, s. So minus sine theta d theta is ds. But I need only sine theta d theta, and that should be equal to minus ds. Then the limits from theta to s. Theta is 0 or pi, so you get cosine of 0, which is 1, or you get cosine of pi, which is negative 1. So what this integration has become, it's plus 144, integration 1 to negative 1, cosine square theta is going to be s squared, sine theta d theta is minus ds, plus this one you get 432 again over 3, and theta is just pi. And we're going to complete the rest of the antiderivative. So now we are going to get negative 144 times, this negative will come out, make it a positive. Cosine of pi is negative 1, cosine of 0 is 1. And then you get minus 144 s to the power 3 over 3, limits are 1 and negative 1, plus 144 pi. So I get minus 288, and then I get minus 144 over 3, and negative 1 to the power 3 is negative 1, 1 to the power 3 is 1, plus 144 pi. We're almost there. So now I get to say that this is negative 288 plus 288 over 3 plus 144 pi. Which is negative 288, and if you do 288 over 3, you get 3 times 9 is 27, so 96 plus 144 pi. So 8 minus 6 is 2, 28 minus 9 is 19, so this is minus 192 plus 144 pi. And that is all we can simplify, and this is the required volume of the three-dimensional object that is trapped between the sphere and the circle.